Decision trees are both a classification and regression supervised learning model used to predict the value of a target variable y using information from several input variables x's. As the name suggests, the model is visually represented as an upside-down tree-like structure, with the dataset being broken into smaller and smaller subsets as the tree grows. Each internal node or decision node contains a simple yes or no question to be answered about a particular x variable. Based on this, the tree splits into branches, one branch representing yes and the other no. At the end of each branch is another question. This recursive process continues, and the tree gets deeper and wider with each decision made until it ends in a leaf node that makes a prediction. Let's take an example dataset. We have the y variable, whether a state is red or blue, and we have three x variables: education, income, and racial diversity. Now let's try to construct a decision tree to predict a state's political leaning, that is, red or blue, based on these three variables. You might wonder how decision trees make splits when a variable is continuous or numerical in nature, instead of being a simple Boolean true or false. The answer is very simple. Under the hood, we create multiple variables that represent splitting the continuous variable at different thresholds. These splits are usually made at different deciles or quartiles of that variable. For our case, let's just use the median of each variable as the single threshold. We'll convert these continuous variables into binary or Boolean variables by setting the value equal to false if the value is less than the median, and true if it's greater than the median. These are now Boolean features. Let's now begin creating the decision tree. To create the first decision node, we have to pick a variable to split on. Decision trees use a criterion called information gain to pick the right variable to look at. Information gain is a measure of how much we know about y after looking at x. For example, if we were to randomly predict the political leaning of a state having no other information, the probability that the state is red is 1/2. However, if we know some other information about that state, we can update our belief about that probability. Let's see what happens when we split the tree at each of our three x variables one by one. When we split on education, we see that the true branch, which contains states with education above the median, has mostly blue states and one red state. The false branch, or states with education below the median, contains mostly red states and a few blue ones. When we split on racial diversity, we see that the true branch, which contains states with diversity above the median, has mostly blue states. The false branch, or states with diversity below the median, has an almost equal number of red and blue states. This means that knowing that a state is not diverse does not meaningfully indicate political leaning. Finally, let's see what happens when we split on income. Here, the true branch, which contains states with income above the median, has mostly blue states, and the false branch, or states with income below the median, has an almost equal number of red and blue states. This means that knowing that a state has below median income also does not meaningfully indicate political leaning. After comparing each possible variable to split on, the decision tree picks the one that leads to the purest branches. In our case, splitting on education leads to the purest branches because the true branch contains only one red state and the false branch contains half as many blue states as red ones. The information gain from education is high. Splitting on racial diversity would have been the worst choice. Although the true branch contains mostly blue states, the false branch is basically 50-50 red and blue. Knowing the state lacks diversity adds almost no new information to the model. The information gain from racial diversity is very low. After making the first split on education, we now look at the two resulting branches, and once again look at which variables we can split on to further purify our branches. This continues until we reach pure branches or the maximum depth of the tree. Our final tree looks like this, and it has an accuracy of about 80%. This is awesome, considering we only had 3 variables to work with. You might ask why we don't simply split on every feature and make the tree as long as it needs to be to get a model that perfectly fits the data. This isn't a bad idea if you have a dataset that is super representative of the population that you are studying. However, the problem with that is that your model might start to make so many splits that it learns the quirks of your particular dataset and fails to fit additional data or make reliable predictions. This is such a common problem that it